not originate from the charge. So origin is not the charge, right? That's another point here. So who is origins? Okay, we'll come to this origin here. Origin is my magnetic fields. We come to the origins. But remember that it is not a coulombs. So not from the charge. Not from the charge directly, you can say here. Indirectly, yes. Directly, not from the charge. Indirectly, it is from the charge. Second important characteristic here is because it is not a Coulomb field. Okay, it is not a Coulomb field. So it's not going to be have a potential concept. It is a non-conservative. It is not conservative. It is non-conservative. It is not a conservative field. Non-conservative. Non-conservative, you know, work done in the closed loop is not zero. Okay, work done here in the loop is going to zero. Imagine it is going to be a conservative. So suppose it is going to be a conservative. So if it is a conservative, let's say it is going to be a conservative and you take a loop. Imagine it is a conservative. Actually, it is not. But imagine, just take a case, it is conservative. Suppose it is conservative. So if it is a conservative, then the work done in the closed loop is going to be zero. If it's a work done in the closed loop is a zero, so it's a EMF should be here zero, because what is EMF? EMF is nothing but a work done, and my electric fields is nothing but a force. It is a force. So E dot dl is nothing, it represents my work only. It is a work done by 1 Coulomb charge. So this represents my work only. If it is zero, then your EMF must be zero. But our basic definition is that it is creating the EMF. So because EMF in the closed loop is not zero, so this line integral in the closed loop is not zero. So work done by this electric field is non-conservative. Okay, it is going to be non-conservative. You can take it's a force like a normal electric field, Q times E, and work done here as F dot ds. It is E dot dl. Okay, star, just to differentiate it here. So in my closed loop, if you find out here the work done in my closed loop, so work done in my closed loop per unit charge. So work done in my closed loop here per unit charge, that is going to be here my EMF. That's my EMF. That's my EMF. And this EMF is according to Faraday's law. How much is that EMF? This EMF is not zero, right? This EMF is not zero. So it means work is also not zero. So it is non-conservative. So when it is a non-conservative, it also give me here one more interesting thing. Conservative fields has a potentials, right? So it's non-conservative. So there is no concept of potentials. So it has no concept of potential. Okay. So potential, when I say potential, I means potential energy per unit charge. Potential energy means it can save the work. Okay. So here potential energy, the concept of potential is coming because of the saving natures. So no concept of potential here means no saving of work. It will do the work, no doubt. It's doing a work. That's why the EMF is coming. But this work is not saved. You can't save that work. Okay. So it is pushing. So as long as it is pushing the charges, work is going on. But it is not going to be saved. Okay. Like my electric fields, like my normal electric fields. So work done is not going to be saved. It's doing a pushing and this work is lost, like a frictions. It's a work done and it is over, right? So as the friction do the work, it will keep on pushing you. It can give you the energy, but after that, that it is not going to be a save. That is the meaning of no concept of potentials. Work there, but no saving of the work. Okay, I hope you understand the point. Yes, no saving of the work, and let's make it here very interesting one. No saving of the work. So one more point. This thing is enough. So it is non-Coulomb field, not originated from the charge. It is non-conservative. Okay, and there is no concept of potentials. So from where it is originated? Who is the source? That is an important question. Who is the source? So I can say it's the source. We can get it the idea from the our Faraday's laws. So my Faraday's law says that if there is a loop, okay, that's my loop is theirs, metal loop is theirs, and there's going to be a magnetic fields. Magnetic field is here, it's crossing over this one. Now this loop is at rest. It is at rest relative to field. So if I say it is at rest relative to field, I mean to say that there is a no motional EMF possible here. Because motional EMF is coming if you have a relative motions. If you have no relative motions, so no motional EMF is possible. But I'm going to be change the magnetic fields. So as you are changing the magnetic field, vary with the times. So there is a flux change, right? So on this loop, there is a flux change. And my Faraday's law says, what does the Faraday's say? So Faraday's law says that because my flux is depends upon the magnetic fields and nothing else is changing. Loop is not changing, nothing else is changing, only magnetic field is changing. Still my flux is changing. And he observed experimentally that this flux change created the current. Okay, so this flux change d phi by dt, it has changed something. So there is a change in the magnetic fields, and because of this time variation, the magnetic field, there is a flux change, and this flux change has created my EMF. It has created my EMF, and this EMF means work done by something. Yes, EMF is nothing but the work done by something per unit charge. So that something, let me call here is a E. So there's something is that force is theirs. So that some force is theirs, and this work done by the force here is DL. There go S we have taken, DS we have taken for the area. So I'm taking DL for displacements. So this something is doing the work. Okay, and because that something is doing here the work, so this work I can say that. So in this case, I can say here this something has done here the work, and that generated the EMF. So the force per unit charge, there must be some field. That field we call it here as a E, right? So there is a field here E. So that is my Faraday's laws. So in this Faraday's law, I can get here the clue that who is creating this electric field, induced electric fields. So clearly you can see that what is the cause of this induced electric fields. So cause of this induced electric field is my change of magnetic fields. Okay, why my induced electric field is coming? So E star is created by the time variation of magnetic fields. Okay, time variation of the magnetic fields, right? Because we are not able to find out any other reasons. Before this Faraday's law, I can explain from the motional EMF. Experiment 1 and experiment 2 can be explained by the motional EMF. But this third experiment, where conductor is at rest, it is not possible to explain. So only explanation is that this somehow this electric field is created by my magnetic fields. So that is the cause. Yes. Hello, Dhiraj.
Good morning, sir.
Good morning.
Sir, could you please scroll up once? Top one.
I'm just explaining you once again. 1 minute. So
Not
I
this
hope
one,
you
sir.
understand. Yeah. This one.
No, sir. First one, sir.
So once again, you can just see here. So few features you need to be understand about this induced electric field. First one is it is not a Coulomb field. It's not originated from the charges directly. It is non-conservative. Why it is non-conservative? Because of my Faraday's law says. My Faraday's law says that you are doing some work in the closed loop. Work is coming. So work is coming in the closed loop means it must be non-conservative. So because non-conservative here means no concept of my potentials. Now this last point is the most important thing is who is the creators, from where it is coming. So to understand, you have to go back to Faraday's laws. So in that Faraday's law, we are going to the third experimental condition. The third experimental condition, if you remember, I say that there is a no relative motion between the magnetic field and the conductors. So it is at rest. Conductor is at rest with respect to the magnetic fields. When it is at rest, there is no motional EMF possible. It is neutral, so no Coulomb field is also possible. But if we just notice here, flux is changing because magnetic field is changing with the time. So my flux is changing because of the magnetic fields. And this flux change created the EMF that we know from experiment. Experiment has given it. Okay. Experiment has given me that idea. So this is going to be here my EMF is there. EMF means some work is being done. Yes. EMF here means someone has pushed the charges. So there must be some work per unit charge. So my work is not something, some force must be there. So some cause, some force must be there. So this force by charge. So this some field must be there. So this field is not magnetic. This field is not Coulomb. So this is a new type of field. And this field is created by our time variation, the magnetic fields. Right? So who is the source of my induced electric field? Source of the induced electric field is my time variation magnetic fields. I hope you understand here the reasons, right? Very good. Okay, beyond that, it is go something about syllabus, after the syllabus. If I ask you what is the value of this induced electric fields? So the value of this induced electric field is going to be go beyond our syllabus, but in one special case, we can take it. So only one special case. Okay. So induced electric field and inside my solenoid only. So that case we have in our syllabus, we can only deal with that. So induced electric field in solenoid, in solenoidal field. So how to find out here the induced electric field in the solenoid is? Solenoid, we can draw here the solenoid pictures from my top view. Basic structure is going to be like that. Okay, if I'm going to make it here as a side view. So magnetic field in the solenoid is going to be along the length. So here, I'm just taking here, this is my magnetic fields, right? This cross here representing my magnetic field. Outside the solenoid, there's no magnetic fields. So only in this limited zones, we have a magnetic field is there with the radius R. Okay. What is this? It's a solenoid. So outside solenoid, there is no magnetic fields. Inside solenoid, we have magnetic fields, right? And this magnetic field inside the solenoid is simply depending upon my current. And current is very easy to change. Very easily you can change the current. So magnetic field is going to be changed. So if there is a time varying magnetic fields, so it will create a induced electric fields, right? So to find out here this induced electric fields, we can take the help of our Ampere's law. We can take the help of this Faraday's laws. So first of all, to find out here this integrals, the integral is going to be such that my dot is simple and E will be out of the integrals, right? So here I'm just going beyond our syllabus in the sense that if we take a circle, if we take here this solenoidals, so in the case of my solenoidal, E star is going to be circulate around the axis of solenoid. Now for this statement, there is no proof in our syllabus, but we just remember this as a fact. How my E star is going to be generated? My E star is going to be circulate around the axis of a solenoid. I hope you understand the point here. I'm not going to prove this statement. This is something comes from outside our syllabus. So it's going to be circulate. So if we take here this loop inside, then how is my E star? It is going to be circulate tangential to this circles. Now this tangential directions, clockwise or anti-clockwise, that we can give here by our Faraday's law, right? That can be given here by Faraday's laws. So if my B is increasing, so B is increasing means flux increasing in the inward direction. Flux is increasing in the inward directions. If flux is increasing in the inward direction, so my induced field must be opposite to that. Okay. So external field here is inward. So my induced or internal field will be opposing that, because external is inward. So my induced is going to be as a dot outward. So I can say my induced magnetic field or internal magnetic field should be a dot. So keeping the dot, you can see here my induced current should be in my clockwise direction, and this induced current is created by our E star. So E star should also be in the same directions. So what are the direction we have for the induced current? Same as the direction of my E stars. Okay, induced electric field. So this is going to be tangential. Once again, I'm telling you why it is tangentials. Can't prove. It is tangentials, right? So keeping this one, okay? Now let's say inside, I'm taking here any loop, okay, with a radius r. So my field lines are going to be here tangentials. Now, one thing which is special about this induced electric field, and I'm sure you have missed the point, is this line, the circle, is not a wire. It is imaginary. Okay, so this loop here is my imaginary loop. It is my imaginary loop, just like Ampere's loop. It is an imaginary loop. Now, because it is an imaginary loop, so this electric field, is that developed inside my metal? No, there is no metal here. It is a space. So it's an imaginary loops, okay? So because it's an imaginary loop, so my electric field developed not in the metal. It is going to develop outside the metal, in a space. I hope you understand the point here. Because it's an imaginary loop, so E star in a space. Okay. So I'm going to apply here the Faraday's law in a space. That's make it beyond our syllabus. We have learned Faraday's law in the metals. But to understand that induced electric field, Faraday's law go into the space. That's why IIT won't ask the question on this topic. Okay, so why it is happening, how it is happening, that's not possible to understand in our syllabus. How can we apply the Faraday's law in a space? When experiment is done in the metals, how can you apply that in a space? So you will understand in your higher studies, okay? For the time being, that's not in our syllabus. So what I'm saying is that's the reasons IIT is not expected you that you have a detailed idea about this E stars. So we have taken here the loop, but this is not a metal loop. This is a imaginary loop. So electric field develop here in a space. This is developed here in a space. Now we're going to be apply the Faraday's law. And we're going to be apply here Faraday's law in imaginary loop. Faraday's law on imaginary loop. So it is applicable. Yes, Faraday's law is going to be applicable. If I apply my Faraday's law on this imaginary loop, assuming that my E star is circular, okay, it is going to be circular. So this side I'm going to be have a magnetic field, rate of change of magnetic field into my area, right? So as a special case, okay, general formula is not in our syllabus. As a special case, if rate of change of magnetic field is constant or alpha, if my rate of change of magnetic field here is a constant, then what will happen in this case? This value of the integrals, okay, we can open here, it will be outside the integrals, and dB by dt is also going to be outside the integrals, and we have this area, integrations on the area. So this side you have a length of the circles 2 pi r. This side you're going to be have a area. Which area is this? That is my area of the flux. So flux area pi r squares. Whatever the flux is there on this loop, okay, inside we have to be only consider. So pi r squares. So I'm getting here the value of my E star, and this value of the E star is your dB by dt, how fastly a magnetic field is changing. And one R cancel, one pi cancel. So it is R by 2. Now it is not any formula. It's not a general formula. Okay? So it's not general formula. So general formula is something quite beyond syllabus, but as a special case under special conditions, in the case of my solenoid, I have this electric field. Okay? That is the case if you are inside the solenoid. Exactly what happens if you are outside the solenoid? If you are outside the solenoid. If you are outside the solenoid, so only change here is my flux is up to my full radius. That's it. There is no further change here. If you are outside, then what is the area? Flux is only up to my capital radius. That's it. If you are inside, my flux is up to the small radius. If you are outside, flux is up to the full radius, right? This side you're going to have 2 pi r. So my electric field outside is slightly different from the electric field inside. So it's a r square by 2r dB by dt. Right, I hope you understand the point, yes? So lot of twists are there in this derivations, okay? Not a perfect derivation, lot of twists are there in the derivation. The first twist here is that this is not general formula, it is only for solenoid. It is only for solenoid, and in that solenoid, electric lines are circulars around the axis of solenoid. That is the first assumption we have taken. Second assumption I have taken is we apply the Faraday's law on the imaginary loop. Okay, on the imaginary loops. So I assume that electric field is going to be developed here in my space. So under that assumption, third assumption we have taken, if my rate of change of magnetic field is a constant, if it is going to be constant, and my B and the area in the same directions, in that situations, I'm getting one special field values, okay, as a special case, not any particular general formula. Yes.
Sir, what is difference between B internal and E star, sir? B internal is created due to the flux change only.
Repeat again. E internal.
B, sir. B internal and E star.
B magnetic field. Magnetic field created by the current here to oppose the flux change. External field is creating here the flux, and this external field is increasing. Okay.
Yes, sir. So
this is my induced current generates some magnetic field. So that I'm calling here as a internal. Induced, you can say it as an induced also. Induced magnetic field is created by the current, and this induced current is created by the induced electric field.
okay.
Right?
Okay. Sir, no need
So,
to
I hope is it okay? Clear?
derivation. Direction. You should just take that, sir.
Direction, you can find out the direction of the E star the way you apply the Faraday's law, Lenz's law, according to the Lenz's law. Okay. So E star direction is same as Lenz's law give the direction of current.
Yes.
Nicholas point one. If you want to write down here, the direction is given by Lenz's law. So no new rule is there for the E stars. Okay? Same Lenz's law give me the direction of this E stars. We are going deeper into the Faraday's and Lenz's law. No? Who is the cause of my Faraday's law? So direction, ultimate directions you got is the same Faraday's law. So E star is creating my Faraday's effects, right? So I hope is it okay, clear? In this derivation, anyone have a doubt here? Understand? A plus point of the derivation is it is not for the conductor, it is for insulator also, because electric field exists in a space. So even the insulators also satisfy your Faraday's law. Even though Faraday's law has not been, experiment is not done on the insulators, but this induced electric field say that the nature support the Lenz's law. Even the insulator is also going to be support here the Lenz's law. Now, one simple questions you can give me the answer here. Suppose we have solenoid. Okay. Inside the solenoid, we going to be have a, let's say solenoid is there. Inside the solenoid, you have current I naught is flow. Number of turn is N, the number of turns. And inside the solenoid, we're going to be have a charge ring is placed here. So this is my charge ring. And this charge ring is made up of insulators. Small r. Radius of the solenoid is going to be my capital R. That's my charge ring. Total charge is Q. A charged ring is placed inside the solenoid. Inside the solenoid with the same axis. Okay, both are coaxials. Ring and the solenoid is coaxials. I hope you understand this. Now, if current in solenoid is suddenly, not slowly, suddenly, if the current in the solenoid is suddenly change or suddenly fall to zero, suddenly fall to zero, find the okay, चलो बोल देते हैं. Find Find the angular speed of ring. Find the angular speed of ring. CAD question itself has given you the idea. Almost half solution is going to be gone in that questions. So what I wanted to ask here is that if I'm going to be placed a ring inside the solenoid, and this ring is inside the solenoid, and suddenly you change the current. So what is the effect happen on the ring? Okay. So this ring began to rotate. This ring is not going to be stationary. No one is touching the ring, but still it has begun to rotate just by changing here the currents. Very strange and interesting phenomena is this. This chapter itself is going to have a lot of strange phenomena. So why this ring is going to begin to rotate? First of all, we need to understand that. So the reason is that this time varying current generate time varying magnetic fields. So because it generates time varying magnetic field, and this time varying magnetic field generate our induced electric fields. So time varying magnetic field generated by induced electric fields, and this induced electric field can exert a force on the charges and torque on the charges. So as a result, it is begins to rotate. Okay, it's going to have begun to rotate. So I hope you understand the point here. Is it okay? Clear? Understand the reason here why ring rotates. The ring rotates because of time variation of magnetic fields. So here you can also think this way, that it is a charge. The charge is moved by the magnetic field. Indirectly, yes. Indirectly, yes. But this magnetic field, I told you, from our definition point of view, again, nature does not make a difference, but we as a human being, we make a distinctions. We have make a distinction that B means moving charge. B is for moving charge. E is for rest charge. For nature, B and E are not separate field. It is the same field. So that is our problems. Understand here? So from the nature point of view, so this moving charges in the wire, they created the current. This moving charges has created the magnetic field, and this moving charges has created the time varying magnetic field, and this moving charges has created the induced electric field, and this time varying electric field moved the stationary charges. So this current, which is the moving charges, so inside the current we have moving charges, and this moving charges move the ring charges. That's it. The charges in the wire move the charges on the ring. That is what is the overall phenomena, right? But we analyzed in this way that current created the magnetic field, time varying magnetic field created the electric fields, and this electric field is going to be generate force on the ring. That's our approach of analysis. I hope you understand here. Understand? Is it okay? Clear? No confusion? So is electric field and magnetic field separate? So naturally it is no, but from experiment, it's we have separated them. We have separated their properties. So because we have separated their property, we analyzed as a separate part. So for us, yes, it is. So how much torque it will experience and how much speed it will gain, we can easily find out here. So let's say there is a everywhere magnetic field is there. So yeah, that's my solenoid is there. Here is my solenoid. So inside the solenoid, I'm going to have a charge ring is there. So that's my charge ring. And this charge ring is going to, we have given here this charge on this charge ring, right? And this charge rings is going to be experience of electric fields. And the direction of electric field is according to Lenz's law. So here, according to my Lenz's law, you're going to be have a induced electric field in this way. So they're going to be everywhere circular electric field is there. Right? Electric field is there tangentially. So now if I'm going to be take any piece just a small piece, if I'm going to be considered, let's say is a dq. So this dq is going to exert a force. And how much is my force on this small dq? So it is going to be a force of my dq charge into the E star field, right? Oh, yes, Shiva.
Sir, here current is decreasing, no, sir?
Current increasing or decreasing? Yes, yes, yes. It is decreasing.
E star will be
Ah,
reverse.
yes. Oh, yes, you're right. Current is decreasing, so direction is reverse. Correct. It's a decreasing, so my E star, according to the Entence's law, it will be reverse. E star is going to be on my reverse side. So anyone have a doubt why it is reverse? Try to apply here this Faraday's laws. In this question, direction doesn't play a much important role. Yes, Akash.
Sir, why the direction change, sir?
Direction in our questions, actually, current is decreasing. It goes to zero, na? So my external magnetic field is decreasing. Okay? It is decreasing. It's a decreasing, and my internal magnetic field or induced magnetic field will be opposite to that. So it is inward and it is decreasing. So my induced magnetic field should be supported. It is not going to be opposite. It is going to be supported because B here is decreasing, right? So I should get here cross. Induced magnetic field should also be cross. And for the cross, I can say my current induced should be clockwise, or in the same direction, you're going to be have a E star. Okay. Flux in the inward direction is decreasing because we have stopped the current. So direction of my induced electric field is going to be clockwise. Everywhere it is clockwise, right? So we can take here one small piece. If I take here the small piece, on the small piece, I'm going to have a force, and this force is dq into E stars. And this is also giving me a torque with the radius smaller. So what is my torque here, Vida? It's R into df. And what is our df? It is dq into E stars. And E star, we have found out already what is the value of E stars. The value of the E stars, we have found out. It was inside, it is R dB by dt. That's my E star inside, if ring is inside. If the ring is outside, we have different formula. Okay? For inside, it's R by 2 dB by dt. So that's our torque. Torque generates alpha. So this is going to be having, you can take it here separately here. Torque is this. That is a torque generated by my small piece. So all are generating the torque in the same directions. All try to rotate here clockwise only. Na? This force, this force, this force, this force. Every part experience the force, and all the forces try to rotate in the same way. So if I write my net torque, so it is a total torque. Right, total torque here. So R square by 2 dB by dt, here is a constant. So only integration left on by dq, that gives me total charge. dB by dt into total charge. Okay? That's the value of my torque. The next thing you can say here is, for this torque can give me the angular acceleration also. We can give here angular accelerations. Angular acceleration is torque is I alpha. So from these relations, tau is equal to I alpha. I can get the value of my angular accelerations. Here I is the moment of inertia. Remember what is moment of inertia for ring? moment of inertia for the ring, it is m r squares. That need a mass also. Okay, mass of the ring is required. So along with the charge, you can take the mass of the ring also as a m. Okay, we don't want here this angular acceleration. We want here the final angular velocity. So it's quite easy. You can do the integrations. Alpha is d omega by dt. And I can take it as r square by 2q divided by I. I have taken the downside. And dt is going to be cancelled out. So if you now integrate on the two sides, so d omega is r square by 2q by I. I is going to create a confusion with the current, so we can take it here as a mr squares. Right? m r squares. M small r squares, sorry. Ring radius is small r. M r squares. So once again, you can see how the things are getting connected. If I'm going to be here change, initially you have some B and finally magnetic field goes to 0 in the solenoid. Na? So my omega, it will go from 0 to final omega. So final omega, I can say it's a r square by 2. R is cancelling. So it's a q by 2m. Q by 2m. And that's a change in my magnetic field. Okay, change. The change is here in the magnetic fields. Right? It's going to have a change in the magnetic field, and this magnetic field change is my 0 minus B naught. So it's giving me a minus Q by 2m into B naught. So remember this ratio, Q by 2m, gyromagnetic ratio. So that here is my gyromagnetic ratio. So once again, your gyromagnetic ratio is coming into the play. So this side, on the left side, you have a rotation terms. My angular momentum depends upon the omega. And this side, you have a magnetic field terms, so which come from the dipole moments. So again, this mechanical part and this magnetic parts are connected by this gyromagnetic ratio. Okay, this B is the magnetic field of my solenoid. And the magnetic field of the solenoid, we have mu naught Ni. We can put the value of the magnetic field of the solenoid, and that gives me the final value of the omega. Now, negative sign here simply indicate that my magnetic field is omega is opposite to my B directions. That is the only meaning of the negative signs. Omega and B, they are opposite. Means the direction of my B due to the current, so you have magnetic field along this axis. So omega, you are going to be having the opposite directions. Okay? So that is the only meaning of negative signs. So just if we take about magnitude, so magnitude here, I can say it's my gyromagnetic ratio, and change in the value of our B change. So in short, here you can say omega change is gyromagnetic ratio into my B change, magnetic field change. That is our simple direct relation we're going to have. As such, we don't have any law to relate the omega and the B. Okay, so I don't want to write it here as a law. Okay. The procedure is important here. In this procedure, what we have learned is why the ring is going to be rotate. So at the mechanical level, at this charge levels, so it is a magnetic field created the electric field, and electric field is going to move the charges, so that charges is going to be generate a current. and these moving charges are going to be oppose the change in the flux caused by my solenoid current change. So see how things are going to be connected, how this nature is going to be connected. And the purpose of the connection is why they are connected. To oppose the flux change. Okay? Purpose here is to oppose the flux change. Lenz's law, that is the whole purpose. I hope you understand, yes? Oh, yes, Sai. Good morning. So anyone have a doubt up to this point, yes? They will understand the reasons. Okay, don't understand here this problems. This is going to be of syllabus problems likely. No chance of getting into the IT. In your Narana paper, weekend exams, definitely this problem will come. Important here is to understand how the nature is connected. Okay. So to maintain here the flux constants, the nature play the same role as to conserve the energy, to conserve the momentums. So flux conservation is also one of the principle of the natures, which is beyond our syllabus. So yes, Shiva.
It means when the magnetic field is changing with respect to time, there will be no translation motion, sir.
Whenever the magnetic field change, purpose is to satisfy the Faraday's law. Okay?
Yes, sir.
And ultimate end result is satisfy the Faraday's laws. So for that purpose, whether it gives translation, rotations, that depends upon the situation. Different problems have different effect. But end result is to satisfy the Faraday's law. It can rotate, it can translate, it can do anything. Okay. In whatever way your flux going to be constants, flux change is opposed in any manners, flux change is being opposed, it try to do anything. It can generate electrical effect, it can generate magnetic effect, it can generate mechanical effect, it can generate thermodynamic effect also, but it will try to do it. Okay, try to oppose the flux change.
Okay.
So there is no clear-cut answer for your questions. Just keep in the mind that time-varying magnetic field create electric field, can create electric fields. That is important thing.
Okay, sir.
And where is that electric field created? Not in the metal. Not in the metal. It is created inside our space. It is created inside the space. Right? I hope you understand the point here. The second question in same one, you can apply here the same question. Suppose ring size is big and my ring is outside. If my ring is outside, so what happens? Outside there is no magnetic fields. So will the ring rotate or not? Case number 2, you can consider here case number 2. If ring radius is bigger than the solenoid radius, then find the omega. How you got the E star? We proved to kiya beta. We have proved it, na? So if ring size is greater than my solenoid, then what happens? So in first attempt, if we try to think, answer seems to be 0. Why? Because in solenoid, outside magnetic field is 0. There is no magnetic field outside. So if I say my ring is outside, you will feel that there is no effect. Solenoid effect is only inside. Okay, so we can feel that there is no effect on these charges. Okay, we can feel that there is no charges, no magnetic field outside. Solenoid has no effect, no magnetic field outside, so it will be 0. But we have discussed already, beta, even outside the solenoid, your magnetic field is 0, but E star is not 0. So there is an electric field outside the solenoid also. So it's not that if there is no magnetic field, there is no E star. E star originates from the change of magnetic fields, but it is not exactly at the same way. It's just like current is there. So magnetic field is around the current. Okay? So magnetic field is created by the current, but magnetic field can exist in the area where current is not there. So at this particular point, I don't have a current, but magnetic field is there. Same way, we have magnetic field only changing inside the solenoid. Okay? So just like a current, my magnetic field is changing inside the solenoid. But my electric field is going to be still exist at a point surrounding it. So my electric lines are going to be circulate around the solenoid. Okay, it is going to be circulate around the area in which magnetic field is created. Magnetic field is changing. I can go to the region where magnetic field is not 0. So it is possible. Just like the relation we have in the current and magnetic fields, the same way we have the relation between the E star and the B derivative, right? So here my B derivative, rate of change of B, it's a play the same role as my current. It is 0 outside, but still E star is there. I hope you understand the point here. Still E star is there. So meaning thereby, yes, the ring is again going to be rotated. Same derivation you can apply. There is a magnetic field only inside my solenoid. So outside we don't have a magnetic field, but there is a E star. So direction of the E star is same outside also. It's given by Lenz's law. Okay? Apply the Lenz's law, you get here the directions. In this problems, your magnetic field is decreasing. So my induced magnetic field should be support. And to keep here the support, my E star is going to be coming in the direction of my clockwise sense. But how much is my E star outside? E star outside we have derived it from the Faraday's laws. If you remember the results, well and good. If you don't remember, you can easily derive the value of my E stars, not a big issue. So my Faraday's law says that EMF is d phi by dt. EMF here is E star dot dl. Now in these derivations, you can keep here the sign. The sign is going to give me here this value. It's a dB by dt dot area with negative signs. Okay. So in this derivation of my E star, this negative sign play roles. So here, along with the magnitude, the sign is also going to play important roles to give the directions. E star is everywhere tangential. So on this loop, if I integrate the electric fields, so E dot dl. So dl integration give me a circumference. dB by dt here is constant or whatever is that. It will be out of my area. And what is this area? It's the area of my flux area. So flux area is only up to my capital R. That's pi r square. So I can say E star is equals to minus dB by dt. Pi cancel out. So R square by 2r. That's my electric field outside. Now this electric field has an impact. It will give me a force on this charged particles. And this force on the charged particle is going to give me a torque about the center line. Right? So net torque, I can say it is going to be the torque exerted by the small piece. And what is the torque exerted by the small piece? Okay, that's going to be here my torque executed by the small piece. You can put the value of this E star. So here, if we keep here my dq, E star value is minus dv by dt r square by 2r. Now this torque is the torque of my force. Okay? It's going to be here my force torque is theirs, and all torques are going to be add up in a directions. Anything cancel out? Yes. My small r here is cancelling out. Now this integration is on the charge elements. So here, charge element you are integrating. So in this integration, the time variation of magnetic field does not play any role. You are taking the integration on the small pieces. So time has no roles. So time is out of these integrations. So dB by dt, even though it is a variable, but it is not going to be play any role in the dq integrations. So in the dq integration, time variation is a constant. So it will behave as a constant. So that will give me just a total charge on the ring. So you can say torque is equals to minus q r square by r dv by dt, right? In last question, I have written that tau is equals to I alpha, and from alpha we get here the omega. There is one more way we can do it. I can just integrate the tau on the time. Right? Now, what is this integration means? That integration means our impulse, torque impulse, angular impulse. That is our impulse. Impulse is going to be here my, it's a angular impulse is there. Okay? So change in my angular momentum. So it is minus q r square by r, and that side comes out to be here, change in the magnetic fields. So change in the angular momentums is related to the change in your magnetic fields, right? Here we want here omega. So initial omega, let's say 0, and finally you're going to have some omega. So this side, finally omega is 0. Finally B is 0. Magnetic field finally 0, because current I told you, no? In my solenoid, current goes to 0. So magnetic field in the solenoid ultimately goes to 0. Right? So it is a magnetic field of my solenoid, mu naught and I naught. This I stand for your moment of inertia. Moment of inertia is mr squares. And this side you are going to have minus plus q r square by r, and b naught here is mu naught I naught. So omega naught just comes out to be this factors are going to be have q by m. I think somewhere we missed the factor 2. Yeah, then I 2 here. That was the factor of my 2. Here it was 2. So we have missed here the 2. I missed you 2. So here is 2. Right? This is my 2. Okay, anything else left here? We got the q 2. Okay, here is my r square, right? R square divided by small r cube, right? So it is here mu naught and I naught. That's my simple and sweet little expression for the omega. And I hope you understand here the procedures. In none of this situation, you need to remember any formulas, only just remember here the procedures. Yes, this concept is not in the IIT syllabus, but in the books you will find the questions. Yes, Vamsi.
Sir, there should be no small r in the denominator, sir. It is cancelled, sir.
Small r cancel. कहाँ cancel हो गया?
In second step, sir.
Okay. Small r is also cancelled. You're right.
So r square by small r square only will be there, sir. In final step.
Take care. Anyway, I hope you understand, catch the procedure, right? Understand here the logic? Yes, Shivaji.
Sir, in the derivation, we got E star value as positive, sir, but in the question we had taken negative, sir. What will change the answer, sir?
Here, if they are asking about the directions, so I have not paid much attention on the directions. I have just made here on the magnitude only. So if they are asking about the direction, so direction we can give here by Lenz's law. For example, if we say here, what is the direction of my E stars? The direction of E star is going to be according to my Lenz's law. And
Yes.
based on that, you can give the directions. So direction, I have not paid much attention.
Okay, sir.
Okay. So magnitude is like, so direction, why I keep here the directions? So direction, I keep it here because if my derivative, this magnetic field derivatives, it could be positive or negative. If my dB by dt is given, it could be given here as a positive derivative or negative derivative. So you can just change here in that B expressions. That's it. Otherwise, it's not going to have a much role. So that's why I'm telling you here, just to pay attention here on the procedures. Okay? The point is, in this, what we learn from this idea here is, what is the idea we're going to learn here is, so Faraday's law is not just for the metal wires. It is just not for the loop. It is beyond the loop also. It is beyond the metal also. You can apply the Faraday's law in the space also, right? So this phenomena of induced EMF, this phenomena of induced EMF is not just a property of the metals, what we learn from the simple experiments. So after the Faraday, some other experiment is done, and they have done the experiment in the space also. So it is a well-established fact that the time-varying magnetic field creates the electric field. Okay. And after this 1 or 2 chapter, we're going to learn that time-varying electric field can also create the magnetic field. It's a reverse way. So magnetic field can create the electric fields, but after 2 chapters, you learn that electric field can also create magnetic fields. So that has very powerful implications. It's created a very powerful phenomena, and that phenomena you named as a light optics. Okay, electromagnetic waves. So regarding that, we discuss here later. But I hope up to this point, you understand this point, clear? So a weekend exam is up to this topic only, okay? So in the weekend exam, you have Faraday's law, how to apply the Faraday's law, motional EMF, and this induced electric field concept is there up to your weekend exams. Right? So to understand here a little more better, we can discuss some more problems. Few more problems, some interesting problems are there. A lot of interesting problems we have in this topic. So we can discuss some more problems that make it here, the Faraday's law, more better. A very, very important questions which is left to discuss. I just going to explain you in details how the Faraday's law is going to be so powerful is. Very simple questions. Question is that suppose we have a resistance, okay? Simple resistance there, and there is a one rod is there, simple rod is there, and this whole system is going to be kept in my magnetic fields. It is just kept here in my magnetic fields. So there is 2 ways you can create here the induced EMF. The one way is that you can change the magnetic fields, or you can move the rod. So let me consider here this second situation that your magnetic field here is, let's say, changing. I change the magnetic fields. My magnetic field is perpendicular, right? This has a rod, and this rod has a length L, and is also going to have some resistance there. Resistance of the rod here is a small r. We can give here the naming also, rod AB. So length of the rod, this internal part, right? This internal part here is going to be my L. So this length is L. Now I'm going to be begun to change these magnetic fields. Initially, the rod is at rest. At time equal to 0, the rod is at rest. So if magnetic field began to change, if magnetic field is increasing at the rate of alpha, we increase the magnetic field at the rate of alpha, find first thing, it's going to be, first thing here is find the EMF induced, not EMF induced, find the current. Find the current. Second thing is force on the rod. Third thing is find the velocity of the rod. Find the current, force, and velocity. So there is a lot of questions you can find where they connect the mechanics. And when the mechanics is going to be connect, it's going to be get slightly twisted. Okay, so if you understand here how my Faraday's law is to be applied, so you can easily connect it to the mechanics. It's very easy to connect with the mechanics. It's not a tough one. Let's see here in this questions. It's given that once again, the rod is given with rod is given here, length of rod is L, mass is M, and there is a resistance also. Okay. Now whether you take it as a conductor or insulators, is it going to matter? Because we have a time varying magnetic field. So in this time varying magnetic field, this is not at all going to be matter. Whether you have insulator or conductors, it's not going to have impact. Whether you take it as a resistance in the insulator is not possible. So you can think of it as a conductor only. So the first thing tell me here, what is the current developed here? For current, I need here EMF. And what is the EMF here? It's not a motional EMF, right? It is not a motional EMF. So what type of EMF is that? This EMF derived in the circuit is coming because of the time variation of the magnetic fields. So it's because of my induced electric fields. Okay. So EMF is due to induced electric fields. Now these induced electric fields circulate, it is circulate around the solenoid, but here is no solenoid given. We don't have any solenoids. So I don't know what is the pattern. I don't know what way this field star is going to be there. We have no idea. So even though we don't have no idea about these E stars, I know the Faraday's law. So Faraday's law simply says that EMF is d phi by dt, rate of flux change. That could be done here easily, right? Flux change could be done here quite easily because my flux is B into area. Okay, here B into area. So this area, this side is given here L, and this side, you can take this side also. Let's say, take it here as a. So this side is going to be a change, keep on changing. So initial value, I can consider it as a t at time equal to 0. Right? So initial area I can consider here, it's a one side is L and it is T. But is it going to remain is it this gap is going to remain same forever? So my Lenz's law says, no, this length area is not going to remain here same. It's going to keep on changing. The reason, because if there is a current developed in that structures, okay? If my current is going to be developed, so this current will give me the force on this rod. Whenever there is a current and there is a magnetic field, so current carrying wire in the magnetic field experience the force. So this force will change this length. So this D is not a constant thing. It's not going to remain stationary. It will begin to move, right? So for the area, this area is a variable thing here. So I can take here, this is L into X. So time variation here is that B into Lx, right? So X is changing with some velocity of the rod. On this expression, B is changing with the time, X is also changing with the time. B here is changing with the time and X is also changing with the times. So it will give me that EMF is Lx dB by dt plus Lb dx by dt, both are responsible. So here first terms is coming because of the B variations, okay? And this is caused by E star. Second term is coming because of the velocity of my rod. And the second term is coming because of motional EMF. So both of the EMF are responsible for my flux change, right? Both are independent phenomena and both are connected by my Faraday's laws and both can contribute into the net EMF. So your net EMF may be caused by the magnetic field variations and net EMF could be caused here by the motional EMF due to the motion of conductors. And mostly, in most of the time in our natures, in practical life, both are contributing, right? Both are going to have a contribution. So I have EMF that will be Lx dB by dt. And this side you're getting the EMF is Lb dx by dt. So you can get here this EMF is Lx. So what is dB by dt? dB by dt is a constant, right? So we can put its value at the end, d by dt. The dx by dt is velocity. So that's my EMF, right? Okay, we got here the EMF is theirs, but we have resistance also. So the resistance of my rod is smaller and external resistance here is R. So I can replace my rod with the battery effect and plus rod effect. Now, where is my EMF generated? So EMF here is generated by the rod motion also, plus my B variation also. So my net EMF is inside the rod only, we don't know. But in the circuit, it is there. So symbolic representation is that net EMF make a series combination with your R and small r's. So it is not in the rod. So net EMF is not in the rod. So don't apply the net EMF inside the rod. It could be anywhere in the circuit. It could be anywhere in the circuit, but one thing is there in that circuit, as my current is going to flow, battery and resistances and the rod, they're all making a series combinations, right? So give me the value of current. Current here is EMI divided by R plus R. Sorry. Right? You can call this equation number 2 also. The current has many effects. And one of the effects of the current is it experiences force. So if I just analyze this rod, so for this rod, you have a current, and this current is in the magnetic fields. So I have a current is theirs, and this current is going to be in my magnetic field is theirs. So what do you think? This current feel the magnetic force or not? So you experience the force. Bill sine theta. Last week we had discussed here magnetic forces, Bill sine theta. It is going to experience my magnetic force. And this force here is Bill sine theta. Angle between the current and magnetic field is 90 degree. Right? It's going to be 90 degree. So you apply here our Newton's law here. So my Newton's law says the force is equal to our ma accelerations. Now force here is my net force, is my magnetic force in this case. I L B. And acceleration here is dv by dt is my accelerations. So one thing you can notice here, Vidal, this is going to be getting equations where my acceleration depends upon the current. And my current is depending upon the EMF. And my EMF is depending upon these factors. So how much is my current? Yes, how much is the current, Vidal? Current is EMF by total resistance. And that gives me here acceleration to the rod. And EMF, we have found out by the rate of change of flux, even though it is going to be a little complicated. So the expression, I can take it here from the equation number 1. Let's see here my equation number 1. So in this equation number 1, that's my magnetic field. EMF, sorry. That's my EMF. Equation number 3, give me here my accelerations. So that gives me the value of my velocity, because accelerations and velocity, they are related. Constant terms, you need not to be bothered here much. We have many constant terms are there. We can remove all these constant terms. Important term here is the variable terms. So what is my variable is? So one variable here is Lx plus Lx dB by dt plus Lb V. So a lot of constant terms are there. So in this constant term, dB by dt is a constant, right? dB by dt here is a constant. That's given here as a constant. My dB by dt here is constant. My B value, magnetic field value, it comes out to be here it's going to be changed at the rate of my alpha. So B value at any time is going to be alpha t. Some initial magnetic field should be given over here. So B value we can say here is B naught alpha t. So B is going to be a variables, okay? Time variables. X value is going to be here my Vt. Initial value of the X is my t. So it can also be written here as a X naught. X naught here is a d plus Vt. That's my X. So it's turned into a very complicated equations. B naught plus alpha t L by M R plus L. L X value here is a d plus Vt, okay? dB by dt is alpha, and our L B value is B naught alpha t into V. Very good. Okay, let's give me here the equations. This equation gives me here accelerations. So for velocity, I need to integrate. And as long as things are going to be concerned here, I don't think so this integration is going to be possible in our syllabus. So integration is possible if you can separate, okay, by separation of velocity and timing. So the separation is not possible, okay. because my separation is not possible, so this integration is not possible. Right? Okay, why that integration is not possible? Because I have given you this data randomly. Okay. In IIT, they will give you the data systematically. We can't find out here the velocity by integration, but they can ask you the accelerations. Okay. Acceleration is possible. EMF is possible. And current is possible to ask. Okay, more than this final answer, what is important here is the approach, how you are going to be approaching here. It's a very simple approach is this. If integration is possible, result is also going to be simple. But in this situations, in this particular examples, integrations goes in a range where it is impossible to be solved in our syllabus. Oh, yes, sure.
Sir, if the rod is vertical, then we get the influence of the gravitational force also, sir, on the rod.
They can give, fine question, they can give, add up here the force, gravitational force also.
Okay, sir.
Okay, I hope you understand here this problems. In these problems, what you have to be learn is simple approach is going to be learned here. So there are few things you need to be pay attention in these problems. The first thing and the most important thing to be pay attention here is my d5 by dt. It will give me the net flux change, net EMF, and that net EMF may be caused by your B variations or by movement of the conductors. So velocity can also be responsible for my EMF. That's my motional EMF. And this time varying magnetic field can also be possible for the EMF. That's my E star cause the EMF. Right? चलिए तो questions का जो data है, इसके data is getting here very complicated. So I give you another problem with a simple data. But approach is going to remain the same. I hope you understand the approach here. Better रहेगा हम इसमें assignment में से लेते हैं ठीक है. So I given you the assignments. So from the assignment I given lots of questions. First you can try here this question number 10. So this question is almost similar one is here. It's going to be try to connect here mechanics and your EMI effects. In your exam, LR circuit is not there. We have LR circuit in the teaching schedule, but not in the exams. Okay, see Avida. Hey Shiva.
Sir, in the syllabus it is given, sir, for exam. Babji sir sent sir syllabus.
For exam, it was
Yes,
there.
sir. Yes, sir. LR circuit, LC oscillations and something.
So when did they send it?
Sir, I will send to you, CC.
No, schedule I have in that schedule, it was not there. Chalo, okay.
Sir, general-
Okay. LR circuit is going to be very complicated. In 1 week, this topic is going to be very complicated. So, अभी फिलहाल इस पे focus करते हैं. Just try to just focus to this point here. So we have a constant force is being applied on a rod length L kept at rest on the two parallel conducting rails. and he is saying a uniform magnetic field is there and force is also there. So first option is asking here is the power delivered by the force will be constant with the time. Is that right? Power delivered by the force. For the power, what is the conditions for the powers? To have a constant power, I need here constant velocity because power is F dot V. If I keep here the constant force, then I need here constant velocity in the same directions to keep here the power constants. So is that velocity constant or it's variables? It's going to be obviously variable. It is accelerating, then my velocity is going to be here variables. So power delivered by the force will be constant? No. The power delivered by the force will increase first and then decrease. Okay, first increase and then decrease. For that, I need to get the equations. Without equation, it's not possible here. Okay, see here the equation. We need to understand what are the phenomena happening in these pictures. So we have a rod, force is there, magnetic field is there, and resistance there. Now, if we going to consider any length here x, I can say that the movement of this rod is going to change this area. So because it is changing here the area, it will generate here EMF. So this rod is going to give me here that velocity. So two ways you can find out the value of EMF. One from the d phi by dt, I can find out here. So EMF is d phi by dt. Flux here is d into area. dx by dt is the velocity. So I can find out here this is the EMF. Second, I can also find out the EMF from our motional EMF. This EMF is not caused by the change of B. Again, B is constant here. So who is responsible for this EMF? So responsible cause here is my motional EMF. So this same EMF must come from V cross B dot L. If we open the cross, so my V cross B is in the four directions. VB in the direction of my length. So getting the same answer from the motional EMF. So why my motional EMF is matching with the d phi by dt? So reason because it's a constant magnetic fields. So you don't have any of the E stars. So in this problem, there is no cause of the E star is there. No induced electric field is there. So this is generating EMF, and this EMF is going to be generate here current. Right? How much current? The current will generate here is EMF divided by my resistance. Is that conductor or the rod has any resistance? So no, they have not given any resistance. Assume rod is only one resistance here is there, capital R. So I can say my current here is EMF divided by R, right? EMF is BVL by R, easy. Sorry. So next I can analyze here the forces on the rod. So there is a one force is coming on the rod, and this force is exerted by some persons, okay, someone. But second force is also coming. The second force is coming because of the current. Because there is a magnetic field, there is a current. Wherever there is a current in the magnetic field, it will experience our Bill sin theta. So the magnetic force is there, so BIL. So I can get here Bill sin theta. Are they equal? External force and the BIL, are they equal? We have no idea. So we can apply our Newton's law. Net force equals to MA. If we apply here my Newton's law, net force equals to MA. In the net force, we have external force and we have a magnetic force, BIL. That is equals to my MA. Now in this situation, if you notice, current is EMF divided by resistance. And my acceleration here is dV by dt. So equation seems tough, but it is solvable. It is possible to integrate, it is possible to solve. If you notice, lots of things are constants. F here is constant, B is constants, length constants, resistance constants, mass constants. Okay, lots of things here is constant. So we have B square L square divided by MRV. So dV by dt. So if you see this expressions, it have something of this nature. So alpha minus beta V equal to dV by dt. So alpha beta are pure constants, right? It is simply going to be my constant. They're not variables. Okay. So this is my natures. This type of integration you have done a lot. Time you can separate on the one side, velocity we can separate on the one side, integration come in the log form, right? I hope you can do this integrations. So integration is going to be, it's a 1 by log time. So it's a log alpha minus beta v. In the denominator we are going to be have a minus beta, this side is going to be have a t. Limit does also play a very important role here. So limit if I put here, so time 0, velocity was 0. Okay, it was not starting in, it was not moving in the initial situations. At time t, I can take velocity v. Now if I put here the limit, upper limit is alpha minus beta v. Lower limit, it will be here alpha minus beta 0. This beta you can take it on the side here, beta t. I can take your log alpha minus beta v. It gives me here alpha exponential minus beta t. So I got here the value of v as alpha by beta 1 minus exponential factors. So it is exponentially changing, right? It's not a new thing, it's not a strange thing. Nature always preferred exponential variations. Lots of things we have discussed in 11th class, in 12th class, where exponential variation is coming. Terminal velocity you reach exponentially. Okay? If you have two hot bodies, they will reach the equilibriums, temperature reach exponentially to the equilibriums. Then charging, discharging will also happen exponentially. So here also, it is going to be approached exponentially. So whenever something is happening exponentially means it is approaching toward a stable state. And this factors, this exponential factors, this is going to 0 with the time going to the infinity. As my time tends to infinity, my exponential factor is going toward the 0. And your velocity is approaching toward alpha by beta. And that's my maximum velocity is this. Okay, maximum. So how it is moving the rod, if you try to plot here is, my rod began from the rest, but ultimately it is going to gain here the equilibriums. It is going to reach the maximum value, alpha by beta. What is alpha beta? Alpha beta we have just basically, to make here the equation simple, we have replaced the f by m with alpha, and I have replaced this b square L square by mr with the beta. So the point to be noticed here is that its approach, velocity is rising exponentially, and it is approaching exponentially toward a stable state. So what happened to the other parameter like x? My current is also depending upon the velocity. This was BVL by R. So if my velocity is approaching exponentially, your current is also have the same variations. Similar nature, directly proportional. So my current is also approaching here exponentially. It is going to be reached the same way. it's going to be reaching here something maximum current is theirs. Right? BL by R, alpha by beta, 1 minus exponential factors. I have taken the alpha as a F by M. Beta, we have taken the B square L square by MR. So this is my alpha by beta ratio. You can put here the value alpha beta and you can put here the value of the maximum current. Important is there is a maximum current is theirs. Right? But why it approach toward that final situation here, velocity is constants. Mathematically, we understand it, no doubt. Conceptually, what is the reason? If you think from the Lenz's law, what is the reason that is approached toward the constant velocity? When it is approached toward the constant velocities, here it's going to be moving with the constant velocity. So if it is moving here with the constant velocity, you can see that in these situations, your flux is going to be continuously changing. Here, your flux is keep on changing continuously. Because if you are moving it continuously in the magnetic field, so there must be a continuously flux is changing. d phi by dt is going to be constant. So why so that? So the simple reason here is my nature oppose the flux change. When my nature oppose here the flux change, so why it is not making that change to be 0? Why not 0? Why it is just making here as a constant value? So to understand one thing, that in nature, other than EMI, we have other phenomena also. In nature, we have resistance property. In nature, we have metal property. In nature, we have capacitor properties. Okay. So EMI is not the only phenomenon. That's not the only phenomenon. So in this nature, in the circuit, you have a resistance is also there, and it has to keep on satisfy the Kirchhoff law. Okay. It has to keep on satisfy here the Kirchhoff laws. So to maintain here the circuit steady state. So this is going to be reached to the final state which satisfy the circuit. So the end result, yes, nature oppose the flux change, no doubt. Nature oppose the flux change. But it is going to be maintained here our circuit properties. Now this is almost similar to our these situations. Let's say if I say that there is a ball released. Okay. So nature try to keep the momentum conserved. That's the nature property, right? Nature always prefer momentum conserved. That happens always. But in this case, friction is also there. Gravity is also there. So my friction and gravity, they try to oppose it, and ultimately the ball comes to a constant velocity. Okay. So the approach toward the situation where momentum is going to be approached toward a constant range. One level it is going to be range, yes. So it satisfy along with the momentum conservation, it satisfies the other properties also. So almost similar thing, not exactly the same thing, but almost similar thing is happened here. So EMI is the one phenomena, and this phenomena try to oppose the flux change. Okay. So it is going to be in line with the other phenomena, and this other phenomena plus EMI together is going to decide the equilibriums, right? So I hope you understand the point, yes? Okay, understand the point here. Flux change is opposed, but that is not the only phenomena. other phenomena is also dominant. So equilibrium, somewhere balance is going to be maintained. So this balance you can only understand if you analyze all the phenomena together in the circuit. So to understand here, these all the phenomena together in the circuit, we have a LR circuits are there, LC circuit is there. Again, we have LCR circuit is there. So we have circuit properties. So circuit property we discuss here in this next class. Circuit itself is going to be a big topic. So in 1 week complete EMI, so not possible to do it. So should we go to the next problem here? These are simple solved problems. Let me take care of slightly harder problems. You can take this problem number 27. Yes, so try this one. It's almost like our previous problems, but resistance has been replaced by a capacitors. EMI effect is going to remain the same. Circuit effect is going to be slightly changed. So the figure shown P, here Q, R, S is a fixed resistance plus conducting frame in a uniform and constant magnetic field here P. So here is inward magnetic field is given and it's a constant. So means E star is not there. Okay? No E star. A rod EF, its mass is given here M, length is given here L, and the resistance R can smoothly move on this frame. So this rod can move on this frame. The capacitor charge difference V0. Here it is already charged to the potential difference V0, and it's connected as shown in the figures. Okay, we have seen the figures. Find the velocity of the rod as a function of time if it is released from the rest at time equal to 0. If it is released from the rest. So first thing is that will it remain at rest or it will gain the velocity. So a simple reason you can give me that because it's a charge one. So this charge try to come back here. This positive charge try to come here. It try to neutralize. So this rod begins to move in the magnetic fields. Because my rod began to move in the magnetic fields, so this moving rod behave as a battery, so it will create battery effect also, right? So it's going to be change the flux, and it is going to generate here the induced EMF. So there is a two cause of the current. The first cause of the current is my capacitor. Okay, it is the one cause of my current. Second cause of current is EMF, induced EMF. So, but current is something which is a circuit phenomenon. And here my current become more dominating than my EMI phenomena. EMI phenomena is only up to this one part, and the current is going to be connected to this whole part. Okay, so you have to maintain the charge conservation everywhere. No? So who will decide the net current? Circuit will decide the net current. So EMI try to give me the current. Capacitor also try to give me the current. So net current is decided by the circuit. Kirchhoff law is going to decide it. Right? So we can see here one by one how much EMF is created by the rod. So it's a moving rod is there, it is getting, so let's say some velocity is there. So when the rod is moving, this is moving in my magnetic field, magnetic field is inwards. So it's going to behave as a battery in the direction of my V cross B. So V cross B is upward direction. So it's behaving as a battery of V cross B in upward directions. If you taken here this cross, okay, so V cross B and the length, they are in the same directions. If you open the cross, it is 90 degrees. So my EMF is VBL. Is that velocity constant? No, the variable one. So anyway, just behave as a battery. So all this net effect you can think of as a circuit property. So there is a battery effect, there is a resistance effect. Okay, so here is my capacitor effect. So we have some charges are there initially. So the charges are going to be on move and they're coming over their side. So what was the initial charge? Initially, the charge you have was CV naught. So instant charge, I can assume it's a Q. And I can assume current in the circuit I. Direction is my wish. Capacitor applied to give current in the clockwise direction, and this EMF right to generate current in the anti-clockwise directions. Who is bigger? We don't know. So we can take current in our choice. So I can take here, there is a polarity of the resistance. So in the circuit, what is satisfied? Kirchhoff law is going to be satisfied. So we can apply KVL rules here. As we are running in the clockwise directions, I am crossing the capacitors, potential rises, Q by C. I'm crossing the battery, potential fall. And I'm crossing the resistance, potential fall. Polar, I can say here Q by C minus E minus IR equal to 0. Here E is the constant of terms, or variable terms. Is that E constant terms? E is my dVL. Current here is dQ by dt. Here in this equation, you have three variables that is. Q is a variable, V is a variable, and time is variables. One equation, three variables, not possible to solve. Right? That's not possible to solve here. But we can take here one more equation from the Newton's law. So along with the Kirchhoff law, my Newton law also comes into the picture here. If we apply the Newton law, so Newton law says this velocity is given by the force, net force. So you have some current is there. Magnetic field is inwards, so that gives me a direction of force. Right? What is the direction of force? So the direction of my, oh sorry, yeah, we got one mistake we are done. Direction of force. Okay, but okay, we have not done any mistakes. So my direction of force is decided by the direction of my currents. So in a circuit, I have assumed the direction of the current clockwise. So EMF is, we have taken the EMF in the upward directions, but current I have assumed in the opposite directions, right? So force will go according to the current direction we assume, or it will go according to the EMF directions. Force will go according to the current directions, because force acts on the net current. And I assume my current go against the EMF direction, right? I don't know what is the direction of current, but I assume my force will be according to my current directions. So what do you think about this force direction here? I downward, I cross B. So where is my I cross B? I cross B in terms of the right side. So that is the direction of force. If I take that force direction in the direction of I, okay, and this is my Bill sine theta. theta is 90 degree. Okay, clear? We can apply here Newton's law. Net force is equals to ma. Net force is only 1 Celsius, and that's my magnetic force, and the magnetic force is my EIL. MAVI/dt. Current, I don't know the value of current. Okay. We have no idea of the current. We have assumed the value of current, right? We have no idea about this current. So in this case, I can take the value of the current as M by BPL